If we look at the history of mankind, we'll see that materials have played an important role in the development of civilization. For example, you've probably heard of the Bronze Age or the Iron Age. And you could argue that today we're living in the Silicon Age. That is the age where semiconductor materials have enabled us to make computers the size of a handheld computer or a cell phone. And the question is, why is that true? Today what we want to look at are two types of materials and how they're dramatically different. That is the semiconductors, silicon, which has revolutionized computing, and metals like copper, which we use in most common electrical delivery systems, for example, the wires in the walls of our houses, and see how they dramatically differ in terms of electrical conductivity. And so the experiment will be to look at the temperature dependence of the conductivity. That is to see how easily electrons move through these materials at different temperatures. We have two types of coolants, dry ice or frozen CO2. And if we pour some water on that, we can see that CO2 starts to boil and the water condenses above it. This is about minus 20 degrees. On the other hand, we have liquid nitrogen, which, Lauren, you can pour into the styrofoam. Liquid nitrogen is about 10 times colder, minus 200 degrees. And so you have your meters here, which show us the resistance of the sample. And go ahead and see how the resistance changes in the presence of these two coolants.
Okay. So this is metal, I guess like about a meter of metal. And here with the dry ice, it doesn't really do a whole lot. It's about the same. Right? The resistance is right about 6.4 ohms. And the liquid nitrogen, oh wow, it went way down, like about, it went down by about a half, so down to like 3.4. And then when we take it out, it kind of warms up again and starts to go back up towards about 6.
Okay. For metal, we see that when we cool it just a little bit, we don't see much change at all. We have to really dramatically cool it by minus 200 degrees, and then we see the resistance drop. Okay, now Tiffany, you're looking at a semiconductor, and we remember semiconductors are the materials that are used in computers, and let's see how its resistance changes when we cool it down.
It's going up. It started at about 10, and now it's at about 25.
Okay. So we've noticed this is dramatically different. Well, first of all, the resistance is now increasing in the case of a semiconductor. Furthermore, we've only cooled it by about 20 degrees compared to the 200 degrees we needed to cool the metal. So we see that the temperature dependence of the conductivity is much greater in the case of a semiconductor compared to a metal. It's our ability to dramatically control the conductivity of semiconductors that enables us to make computers. For example, on a computer, we know that we encode information as ones or zeros. For example, as a lot of current flowing or no current flowing. This is how a semiconductor works. We control the conductivity dramatically. In the case of a computer, we use an electric field or a voltage. But we can also use temperature. And as a result, semiconductors are also used in, say, thermostats in your house. So Lauren, perhaps you could summarize what we know about the electrical conductivity of metals.
I guess we learned that the conductivity of metals at a lower temperature goes up. So that would mean that it's easier to pass an electrical current through a metal at a lower temperature.
On the other hand, Tiffany, tell us how semiconductors dramatically differ from metals in terms of conductivity.
When we cooled the semiconductor down to only negative 20 degrees Celsius, as opposed to the negative 200 degrees Celsius that we cooled the metal down to, the resistivity went up as opposed to down.
Okay, so today what we've observed is an example of where different types of materials have dramatically different properties. And as material scientists, we strive to understand the relationship between the structure and properties of materials so that as materials engineers, we can design the materials of the future.